Welcome everyone to the presentation of my doctoral defense. I will talk for the next around 20 minutes about flame dynamics and thermoacoustic interaction mechanisms in technically relevant systems and especially about their prediction. So let's move on to the broader motivation for this work. Achieving low emissions will require changes to the combustor design of future gas turbines and the use of alternative non-fossil fuels. This is something what we all know and what will happen. However, there's a problem. These novel combustion technologies are susceptible to thermoacoustic combustion instability, which can reduce operational flexibility and performance and in extreme cases lead to the destruction of individual components or the entire system. The left-hand side of this inequality shown here states that the unsteady flame adds energy to the acoustic field when the heat release rate is in phase with the pressure at the location of the heat source. That means the smaller the phase difference between pressure and heat release rate fluctuations, the greater the energy added to the instability. And it's important to note here that this self-excited instability is unique to each combustor. Consequently, predicting thermoacoustic combustion instability reliably in practical combustion devices remains challenging. Another problem is that the earliest indications of thermoacoustic combustion instability often occur during full combustor or engine testing, and these are typically in the late phase of a development program. Therefore, a thermoacoustic design process for aero engine burners has been proposed recently to confront this issue. And this process is shown here, which is a two-step strategy. In the first step, a reduced order model of flame dynamics is estimated based on measurements and simulations. And in the second step, the acoustic field produced by the flame is assessed by using a thermoacoustic solver. And if the burner design is found to be stable, one can go to advanced testing. If it's found to be unstable, one can iterate. Therefore, there is a growing interest in developing flexible, consistent and accurate tools for predicting flame dynamics with the objective of optimizing stability margins at an early stage of the design process. And this is where my work comes into play. So the key mechanism for predicting thermoacoustic combustion instability is the flame response to flow perturbations, characterized in the linear regime by the flame transfer function shown on the top left within this black box. Another potential driver for thermoacoustic instability in technically relevant configuration is the presence of coherent temperature inhomogeneities in the burnt gas, which are referred in literature as hotspots or entropy waves. I will call them entropy waves throughout the talk. And the response of these temperature fluctuations to upstream flow perturbation is characterized by an entropy transfer function, so a similar concept to the flame transfer function. And within my work, I have focused on both. I've focused on the flame and on the entropy response because the understanding of both responses is essential for developing predictive tools to mitigate thermoacoustic combustion instability. And the thesis is basically comprised of five papers, 4 building blocks, which are shown here. So on the top left, we demonstrated the limitations of the state-of-the-art experimental post-processing approach for determining flame response when applied to realistic test rigs and developed a novel method that circumvents these issues. On the top right, in a numerical study, we demonstrated that acoustic wave propagation in a CFD simulation is not relevant for the identification of flame dynamics, and therewith confirmed that incompressible CFD is a valid tool for such kind of investigations. On the entropy side, on the bottom left, we investigated the generation of entropy waves in detail and isolated the source terms of entropy perturbations using an arbitrary Lagrangian Eulerian framework. And last but not least, we studied the generation, the transport and the dispersion of entropy waves in fully and partially premixed flames and confirmed that equivalence ratio perturbations are the dominant mechanism for entropy wave generation in partially premixed flames and demonstrated the existence of 2 generation mechanisms in fully premixed flames where one of them was previously unknown. Due to time constraints, I can only focus on these 2 building blocks. If you are interested in the remaining 2, I refer you to my thesis. So let's focus first on the first building block. let's think we have that kind of a test rig on the top left. So we have a duct, a burner, and a downstream duct. The test rig comprises an upstream and a downstream siren to modulate the air mass flow at distinct frequencies, and we have arrays of microphone upstream and downstream to monitor pressure fluctuations. When we want to use this acoustic method to predict or to estimate the flame transfer matrix and later on the flame response, we need a concept of a transfer matrix. So a transfer matrix, shown in the block here, is nothing else than a relation between pressure and velocity fluctuations downstream to pressure and velocity fluctuations upstream. And everything in between is basically treated by a black box, and that's exactly what the transfer matrix is. What we can see here is that we can do measurements upstream and downstream forcing, then basically get the transfer matrix from the experiments. This is where it's shown measurement. So everything between upstream and downstream is characterized by this measured transfer matrix. And if we want to model everything what happens between U and D, we can just use that by one burner, which is here denoted as B. When we go to an experiment where we have a flame involved, so on the right side, we can again do the measurements. So everything between U and D is just the transfer matrix, this T tilde superscript H for hot. And when we want to model everything between upstream and downstream, we can just say it's a burner and a flame. And here it already is visible that the measurement already intrinsically describes the flame, because the information of the flame is inside the measurement T tilde H. And if we incorporate the cold transfer matrix into the hot transfer matrix, we end up with a description that the flame is equal to the matrix multiplication of hot matrix times the inverse of the cold, and this gives us the flame transfer matrix. And we call that approach the burner flame transfer matrix, or BFTM approach. And this approach is valid if you have that kind of an academic or that kind of a test rig, typically academic test rigs, simple configurations, and this is where this approach perfectly works. However, we have to rethink if we go to more advanced, to more realistic combustors. So now we don't have a duct, a burner and a duct, but now we have a real aero engine combustor in between upstream and downstream, where we have a flow split. So around, in our example, 70% of the mass flow go into the combustor and 30% go into an outer annulus and through thousands of effusion holes, what you can see on the bottom right, into the combustor, which is used for effusion cooling. So again, we can do measurements, and everything between upstream and downstream can be characterized by this measured transfer matrix, as in the simple case in the slide before. However, when we try to model everything between upstream and downstream, it's not just a burner, what we can see directly from that sketch. Same things when the flame is incorporated, so under hot conditions, we can do again this measurement. Everything between upstream and downstream is just that measured transfer matrix. But if we want to model that, we have something plus a flame plus something. So it's not that obvious than with a simple test rig before, and therefore it already gets visible that the BFTM approach is not valid when it comes to such complex combustors. And in the paper, which is shown as reference to here, we also showed that this approach is mathematically not consistent, and we showed that also with a toy problem. So the reason why we had to modify something is that we want to solve that problem. So we want to get the flame transfer matrix also for that kind of complex combustors, and therefore we developed a novel method. So our method basically requires a connector model which connects everything between upstream and downstream before the flame and after the flame. And this can, for example, be a low order network model where everything between the upstream and right before the flame and right after the flame until downstream is modeled with a network representation. And when we want to apply this to real data, I will show you on the next slide how this method exactly works. So for our method, we need two ingredients. Ingredient number one is the transfer matrix of this connector model. So strictly speaking, this can be just a network model which represents the combustor, the geometry between upstream and downstream. The second ingredient is this measured transfer matrix, as we already heard that before, which intrinsically has the information of the flame inside. For our approach, we have then to invert this transfer matrix and combine it with the connector model. That means we close the network model from the state D to the state U with a measured transfer matrix. And when we now inversely solve for the element between P and R, we end up with the inverse of the flame transfer matrix. So we can again invert that, end up with a flame transfer matrix, and have exactly what we want to have, which we can optionally also, or where we can optionally extract the flame transfer matrix out of it. Our approach is called model-based inference because exactly of the reason of ingredient number one, it's model-based. So in addition to the experiment, we need a low-order model of our combustor. And we use that methodology then or we apply that to real experimental data. And we use therefore the SCARLET, which is an acronym for Scaled Acoustic Rig for Low Emission Technology from Rolls-Royce. And this test rig comprises a test section which is a full-scale single-sector aircraft combustor, and the whole rig is operated under realistic engine conditions, so high pressure, high mass flow, high preheating. And when we compute the flame transfer function now with a standard approach, which I showed before, and with a new approach, which is mathematically consistent, we can see that there is a discrepancy in the phase and in the gain. The phase somehow looks similar, however that can just be a coincidence. And for the gain, at least above Strohal number 3, there is a large discrepancy. And it's important to note here that compared to the standard approach, so to the BFTM approach, the model-based inference method is mathematically consistent, and however, it depends on a low-order model and therefore introduces a sensitivity to modeling errors. And if modeling errors are there, they manifest in errors in the flame transfer function. So that means in future work, the models which are underlying this method have to be improved and uncertainties have to be quantified. So I've now talked about flame response, and now I would like to go on to the entropy response side of my dissertation. So this is how a partially premixed combustor looks like. We have from left to right the air inlet, we have then a swirler, we have fuel injectors, and we have flame sitting inside a combustor with cooled chamber walls. So at the position of the fuel injector, we have fuel-air mixture oscillation in such a system, which produces rich and lean pockets of fuel-air mixture, which are convected with the mean flow towards the flame. That means the flame consumes then leaner and richer pockets. That means it instantaneously burns at higher and lower temperature, and therefore produces temperature fluctuations in the burnt gas. Besides what we found in a previous study, when we burn a mixture which is a methane-hydrogen mixture, we also have the effect of differential diffusion of hydrogen, which produces on a local scale also equivalence ratio perturbations and fuel segregation, and therefore also generates entropy waves. And in addition, if we have cooled walls, this effect of wall heat losses also generates entropy waves. And we want to investigate the entropy response of a partially premixed rig with real experimental data, which we can use for validation of our numerical approach. And therefore we collaborated with ETH Zurich, and this is the rig under investigation. So it's a test rig under ambient pressure we have again loudspeakers to force the mass flow, microphones, we have a burner, and we have a two-staged fuel injection. And the most important thing in the experimental setup is that at around 28 centimeters downstream, the burner outlet, we have a laser-based methodology that gives the temperature signal at that certain position, which we can later on compare with our numerical approach. And we modeled in the large eddy simulation everything in the yellow box. So this is our numerical domain, and what you can see at near the outlet, this is exactly the same position as the laser-based method in experiment, and this is where we compare then the temperature fluctuations and basically the entropy transfer function in the end. So the numerical approach works like the following. So we have a computational domain, and now we put broadband forcing at the inlet in order to excite the air mass flow. And such a broadband signal looks like the following. So on the left-hand side, you see the broadband signal in time and frequency domain. Time domain doesn't have too much information here, but the frequency domain, in the frequency domain, you can see that our broadband signals have a high power spectrum until the frequency or until the end of the frequency band of interest. And this is how we construct our broadband signals. And what we then do in the experiment, as I said, we excite the air mass flow and then we monitor the velocity perturbations at the burner outlet. This is our input signal, and the temperature fluctuations at the position of the experiment, which is 28 centimeters downstream the burner outlet, which is then our output signal. And with that, we can construct this entropy transfer function by using system identification, and the result is shown on the left. So what we see here is at the top the gain and at the bottom the phase of this entropy transfer function. The solid line is the result from the simulation, and the dots are the experiments. So what we can see in the gain graph is that it exhibits an overall low-pass behavior due to the convective nature of entropy waves, and it decays towards zero gain after a local minimum. When we go to the phase, we see a steep decline, and an argumentation for the low frequency limit can be brought in here. So the low frequency limit, when we go towards 0 Hertz, can be thought of as a change in one quantity, for example, the air mass flow, resulting in a new steady state of the system. That means if we would increase at the low frequency limit the mass flow rate, we would increase the velocity. That means the amount of air available for combustion relative to the fuel also increases, which brings down the burnt gas temperature. That means velocity perturbations go up, temperature perturbations go down. That means pressure, velocity perturbations and temperature perturbations are out of phase, and the phase of the ETF should therefore go in the low frequency limit to pi or minus pi, which is consistent to numerical results. And if we would extrapolate the experiments, we would end up with a very similar result. However, in that study, we also wanted to investigate the influence, or we wanted to investigate the different mechanisms which lead to entropy waves, which are velocity perturbations and equivalence ratio perturbations. And therefore, we excited the air mass flow with a broadband signal as in the simulation before, and additionally, simultaneously, the fuel mass flow with an uncorrelated broadband signal to the first excitation signal. We then monitored velocity and equivalence ratio perturbations at the burner outlet. These are now our input signals. Because we force now both the air and the fuel mass flow, velocity and equivalence ratio at the burner outlet are nearly uncorrelated, and therefore we can investigate both signals. And we again have the temperature fluctuations at the combustor outlet, which is our output signal. What we can now see here, or what we can now first of all do, is that we construct the following equation, which is shown in the box. That means we have now an individual entropy transfer function for the mechanism of equivalence ratio perturbation generating temperature perturbations, and an entropy transfer function U, EU, which gives insight into the mechanism of velocity perturbations resulting in temperature perturbations. And what we can directly see from this gain and phase graph is that the effect of equivalence ratio fluctuations is much larger than the effect of velocity perturbations. And this is interesting because in our case we already have very strong water cooling, and where we have severe wall heat losses, and we have significant differential diffusion because our fuel mixture has hydrogen of 59% by volume. So that means the effect of differential diffusion and heat losses should be quite high, but equivalence ratio are the dominant mechanism even in that case, and therefore we would or we argued in the paper that the finding is generalizable also to other configuration of partially premixed combustion. And this already brings me to the end of this presentation, where I want now to briefly summarize the achievements of the individual building blocks. So in the first study, we demonstrated that the state-of-the-art approach for determining flame response is invalid when applied to realistic test rigs, and therefore developed a novel method for inferring the flame response in such realistic test rigs. We demonstrated that acoustic wave propagation in the LES is not relevant for flame dynamics identification, at least when we investigate velocity-sensitive acoustically compact flames. And we also investigated a methodology developed a methodology for mitigating self-excited transverse mode, a common problem in compressible LES. We further isolated consistently the source terms of entropy perturbations by tracking the source regions utilizing an arbitrary Lagrangian Eulerian framework, and we confirmed that the perturbed heat release rate per unit mass is the dominant contribution. And the last building block, what we just saw in a couple of slides before, we confirmed that equivalence ratio perturbation is the dominant generation mechanism, even in the case of severe wall cooling or severe wall heat losses and differential diffusion. Therefore, we said that this should be generalizable, and we demonstrated that entropy waves can be generated even in fully premixed flames through wall heat losses and differential diffusion of hydrogen. So this already is now the end of my presentation. Thank you very much for listening in, and I would be happy if you have a look into my thesis.